off the table, I mean. All right. So this, I think, is where we left off. Circuits with dependent sources. We have talked about dependent sources, right? This is not something completely out of the blue. We had some examples with Telegin's, that employed Telegin's theorem that required us to use dependent sources. But we hadn't really addressed it in depth. So that's what we're going to do now. And really, one of the best ways to do that is by looking at an example. So how do we solve these? Let's just jump right into it. Take a look at this example right here. We have a single loop circuit, which is nice. It has a 12-volt source. It has a 3 kilo ohm resistor. It has a dependent voltage source and a 5 kilo ohm resistor. The value of the dependent voltage source is 2,000 times I1. So does anybody remember what the name for that was? There was VCVS, VCCS, voltage controlled current source, voltage controlled voltage source. So which one is this? This is something that could come up on a quiz or an exam. Again, there's not many things I ask you to memorize in this class, but I do expect what limited terminology that you understand what that means. Because you will see it in later classes where they'll just throw it out there. And I want you to be prepared. Yes? It's a current controlled voltage. Bingo. Yes. Current controlled voltage source. Controlled by current, and it's a voltage source. So, the current I1 is defined in a clockwise fashion, and we need to solve. I labeled whatever values were left over. I just gave them the name V5K and V3K, just so we would have something, a name to refer to them by. And we make sure that they adhere to the passive sign convention. The current I1 flows from the positive to the negative terminal of these two passive elements. So, because this is a single loop, we know that KVL will provide the predominant basis for finding a solution, right? For single node pairs, it's KCL. That's the most interesting aspect because there's only one voltage across the terminals. And then for a single loop, KCL is not very interesting because there's just one current. So KVL is the one that we're going to use. So let's write out KVL. We have VS minus V3K plus VA minus V5K equals 0. Just the voltage across all of these elements. VS and VA are positive because they share the same polarity. V3K and V5K are negative because the polarity opposes it. All right, next. We're going to make substitutions to, essentially, we have one equation, and we want to get it down to one unknown. That way we can solve for it, right? Just basic, good old algebra. So what substitutions can we make? Well, VS is nice. We know that's 12. For the voltage across the resistors, we're going to use Ohm's law. So it's 3,000 times I1, 5,000 times I1. And then for the dependent source, it's a no-brainer what the substitution is going to be. We're going to use the dependent relationship. So we plug that in with 2,000 I1. So once you plug in all the values, you'll see that the dependent source actually ends up looking like a resistance, actually a negative resistance because the sign is opposite, but it's just something times I1. So we can collect the terms. What we'll have is minus 3,000, minus 5,000, plus 2,000. So that gives us 6,000, but we'll move it over to the negative 6,000. But we'll move it over to the other side, which will give us 6,000. And what we'll end up with is 12 equals 6,000 I. Or this is a different form here, 12 minus 6,000 I equals 0. Then we can solve. I1 equals 12 over 6,000 gives us 2 milliamps. So now we know what the loop is, what the current is running through that loop. V5K is V times I, and that gives us 10 volts. We could do the same thing for V3K, and that would give us 6 volts. Do all the voltages sum going around in a circle? Let's do a check of that real quick. So we have 12 minus 6 is 4, plus 2,000 times I1, so that will be 4. So this is 6, 4, and 10. So 12 minus 6 is 4, plus 4 is 8. Hold on. No. 12 minus 6 is 6. I don't know how I messed that up. 12 minus 6 is 6. 6 plus 4 is 10, and 10 minus 10 is 0. So it does work out. All right, good. So now let's, again, take a look at another example that has a dependent source in it. What kind of source is this one? What's the name of it? Current source. Yes. You have to split up the two parts of the name in your head because they're different. So VCCS, voltage controlled current source. And this value, we'll talk a little bit more about it later. This is called the transconductance value. And it just is a value we use to represent the ratio between voltage and a current. You know, how resistance can be used to represent the opposite relationship. It's, again, related to the G, the conductance that we talked about when we defined admittance. Okay, so we have this circuit here. It's in two pieces. They're not directly coupled to one another. Yes?
Maybe it's just a lack of understanding. But, so, I understand voltage, but, you would feel voltage, if it went through you. Could you feel current going through you?
If anything, the current is actually what's passing through you. You feel the current. A voltage being applied is merely a potential for current to flow. Again, going back to the water example, the speed at which the water is rushing, that's the current. The lifting the water up to the top of the water tower, that's the voltage potential. It has the potential to flow down, but unless there's a path for it to flow, meaning there's a finite resistance, nothing's going to happen. Okay, so, but that being said, for a human body, the more voltage, the more current there is because there's a linear relationship. So if you were to physically feel it. Okay, so we have these two circuits. And this type of circuit is going to show up often because we're going to use something similar to this, a form similar to this, to talk about amplifiers in chapter, whatever the next chapter is. So get familiar with this form. What we have on the left-hand side is a voltage source, a source resistance, and this measurement resistance, which we're calling R2. Then we have a voltage-controlled current source with a associated resistance, which doesn't exist, it's shorted. And then we have a load resistor. Okay. So I've given you all the values. This current here is equal to GM times V2, whatever the GM value is. And we want to label everything that we don't know. So I'm going to call this VRS. I'm going to call this current here I in. I'm going to call this current here I out. Although we know that I out is simply going to be minus GM V2 because it flows in the opposite direction of the source. I just defined it like this so it would match the polarity of V out according to the passive sign convention. We're going to call this the input stage, and this is sort of some terminology that we take from when we start talking about amplifiers, and we're going to call this the output stage. So let's write out the potential equations that we can use to solve. Our goal is to get the ratio between V out and V in, otherwise known as the transfer function. Yes?
We've gone through like a lot of the equations for this
Sure.
sort of thing. Are they all just derivatives from the simple ones we know of? Or?
Yeah. Really, everything we have used in every single example, every single problem, KVL, KCL, Ohm's law, and sometimes Callaghan's theorem. That's it. So, and I even wrote it right here, right? So for the input stage, let's try writing out KVL. So we know Vn minus VRS minus V2 equals 0. Then I was going to try writing KVL for the output, but we don't know what the voltage is across a current source, right? For a voltage source, voltage is known, current is unknown, and then vice versa. So, I mean, I could make up a name and say the voltage across this source is called Vx, and then write out the equation, but it's essentially going to be just introducing more unknowns into it. So, I mean, you could have written it out, but it ultimately is not going to help. So let's try writing out Ohm's law for the output stage. We know that V out will be equal to I out times RL, and then just real quick, I'll substitute in for I out. It'll be negative GM V2 RL. Okay. So before we start writing more equations, let's see if there's anything about these two that allows us to solve. The good news is that we do have equations with V out and V in. How many unknowns are left? So V2 is an unknown, and VRS is an unknown. So we have two equations. We have two unknowns. We just need to combine them together. And again, one important part of this class, the algebra stuff, there's really nothing I can do to improve your abilities there. You just got to keep plugging away at the homework examples or at the examples in the homework problems, and all those skills will come back. A lot of us, I know when I was taking this class as an undergraduate, I had never used algebra in that depth before, because it was just like, they teach it to you, and but you don't ever have an application where you rely on it this heavily. Okay, so how are we gonna do this? How can we get V out and V in the same equation? And so the answer is we're going to use the common element, which is V2. So we'll solve this right here for V2, and we'll plug it in to the one up top. Right? So V2 is equal to V out divided by negative GM RL. Right? I'll take this, push it over to the other side. And then I take that and I plug it in up here. So I have V in minus VRS minus negative V out over GM RL equals 0. And then what I did was I just took the two negatives away and I made them positives. And so now our V2 is gone. All right, so let's try to get it into the form of V out over V in. So what we'll do is we'll move this over to the other side. That gives us what we see here. We end up with V out equals V in minus VRS. Or sorry, V out over, yes. I took this whole term and moved it to the other side. So V out negative 1 over GMRL equals V in minus VRS. Ignore the green for a second. Now that we have what's in the blue, we want to introduce the V out over V in, so we'll divide both sides by V in. So that will give us V out over V in times this term equals V in over V in minus VRS over V in, right? This will become a 1. Make sense? And then what we'll do is just move this over to the other side to isolate the V out over V in. And what we're left with is negative GMRL times 1 minus VRS over V in. So we're a little bit short of what we need because for our transfer function, V out over V in should be a function of only the static parameters of the circuit, which in this case are the resistances. So we need to get rid of our VRS, and we need to get rid of our VN. So how do we get rid of VRS? It turns out that VRS, well, let me ask you. Let's say you wanted to come up with an expression for VRS. There's some different options that we have, right? Ohm's law is going to be one of them, right? We could say VRS is equal to RS times IN. It's a little bit tricky because if you think about the strategy for the algebra, now we're throwing another unknown in there. Right now there'll be IN, which we got to deal with that. So that stinks. What's another equation we could use to define VRS? So what does this left-hand side of the circuit look like? Yeah, I heard it. I think everyone said it. Voltage divider, right? So VRS, and I know we're used to seeing it, the resistance is switched. Normally we're looking for this voltage right here. But it doesn't matter, right? Where they are. As long as we use the proper resistance in the numerator, we're fine. So VRS will be equal to the input voltage times RS over the sum of the two together. That sounds familiar? And so the nice thing about that expression is it has a Vn in it. We already have a Vn in our equation, so at least it's not adding another unknown. It may be adding another instance of an unknown we already have, but it's not like using Ohm's law where we stick an I1 in there and it's almost like we're digging the hole deeper. And if we get lucky, maybe they'll cancel out. So that's the substitution we make here. VRS equals RS over the sum of both of them together times Vn. We plug that in right here, and we do get lucky. The Vn's do cancel out. Right? This cancels out with this. And then what we're left with is V out over Vn equals GMRL. We did some multiplying by -1 to get rid of the sign. Equals -1 plus RS over RS plus R2. And that's a perfectly fine form of the transfer function. You could just leave it like that right here. But normally there's a couple things that we style-wise try to do. Like I said previously, we always try to take the fractions out of the denominator of a fraction, of another fraction. And then in this case too, if we have the opportunity to combine into one fraction, it just looks nicer. It just makes it shorter. But this is a correct answer because it is a transfer function that is a function of only our parameters, transconductance and resistances. So, but if we wanted to make it look nicer, we can multiply by the common denominator, which is RS plus R2, which that would make this RS plus R2 over RS plus R2. We can combine these two together, and what we're left with is GMRL minus R2 over RS plus R2. So this is the same as this, just looking a little bit nicer. Okay. And so that was the point that we got to at the end of the other section of this class. So any question? Yes?
Yeah. When you solve for, like, when you use the voltage divider equation, I thought R2 was supposed to be in the numerator, not RS.
It's a very good question. Very good question. You have to, like a lot of things in this class, it's a lot of bookkeeping and keeping track of things and making sure you know really what And this is, I think, also why the cheat sheet doesn't necessarily make the problems easy. Because the cheat sheet implies that you have the inherent, very good understanding of why things are the way that they are. So, if we were trying to find V2, it would be R2 over RS plus R2. But there's nothing that says, right, in a single loop circuit, the order of stuff is irrelevant. Okay, we can move things around. So if I wanted to, I could redraw this with this up here and this down there, moving VRS down to the side, moving RS down to the side, and that would be a form more like what you're used to seeing for the voltage divider. You could do that, and I encourage you, especially in the beginning of this class, redraw stuff to fit the form that you're used to seeing it, if it helps. Because trying to do things in your head, we'll do that more and more as the semester moves on, but it can lead to questions, it can lead to mistakes. So that's the reason why it's RS in the numerator. So those are two more advanced examples that deal with dependent sources. Dependent sources don't necessarily make the problem that much more difficult. As you've seen, they just are another equation that we can throw into the mix with our KVL, with our KCL, with our Ohm's law. And it's just getting used to solving it. For quizzes and exams, as we move into more difficult problems, write down what you know. Okay? Write down the process that you would take. When I was an undergraduate, was never very good at getting the correct answer. I guess maybe my mind would go blank on quizzes or whatever. But I was at least, I knew enough to make sure that I could explain to the professor, I know what I'm doing, I know 99% of this, okay, I can't get the algebra to work out right now. But that'll get you a lot of points. So I encourage you to do that on quizzes and exams. Write down your steps, write down your equations, show that you know the principles associated with the circuit, and then maybe if you can't get it to work out completely, you can say, hey, I was 99% of the way there, but algebra didn't want to cooperate. All right. So 10:03. We'll do a little bit more new material, and then I'll stop so the people who are taking the makeup can do so. And what I'll be doing is, we didn't have this issue with the missing arrow in the other section. So in the other section, I'll be going a little bit further. And I'll try to review it quickly at the beginning of the next class, but this is going to be one to make up a little bit of that missed time. Make sure to take a look at the video for this week that I'll be posting, this afternoon. There'll be some stuff tacked on at the end that we didn't necessarily go over in this section. Not too much, probably about 20 minutes, but you should look at that before. Okay, so what we're going to do is we're going to jump into another example. If I can get this pen to work. It says it's connected. All right, there we go. All right, so this is an example. Switching gears a little bit, this one does not contain a dependent source, but it does have an instance where we're going to have to use the delta to y, y to delta conversion in order to make it work. So let's jump right in. And one thing about this circuit is that the delta and the y, it's sometimes going to be presented to you in a form that it's not really going to look like a delta or a y, meaning that it's not going to have a nice triangular shape. So sometimes you have to dig it out. All right. So let me label everything here. We have a 12-volt source. It's 12K, 18K, 6K, 12K, 18K, 6K, 4K, 9K. I'll give the... So step one, eventually I'll stop writing this, but for a little while longer I'll keep writing it. Label everything. We want to have names for stuff, so node A, B, C, D. Okay. And what I'm going to do as far as there's no two, well, I'll write it out. So this is V12K. Or actually, I don't need to write out any names because now I can just use the letters, right? Like this is VAC. This is VAB, right? So I don't need to label the voltages anymore because I can just use that. This is called IS. That's the value we're looking for. And for example, again, we could do the same thing with currents. Like this right here would be called IBD. Okay, next step. So given the tools that we have right now, we're always trying to solve the circuits down into single node pairs, single loops. We keep saying that over and over again. How can we do that? I've already told you that we're going to have to use the delta to y, y to delta conversion. But still, I mean, do we see any parallel or series combos? No, there's nothing that really lends itself. So, what forms do we have? Are they deltas or are they y's? And is there one? Is there more than one? Where are they? So the only requirement for the delta or the y, yeah, go ahead.
Is it a delta?
It is a delta, yes. So the only requirement for the delta or for the y is that, so for the delta, they have to be connected end to end in that triangular form. It's not like series where there's something that says nothing else can be connected to that node. So you can see here that we have a delta here, right? That forms one delta ABC. And then we actually have another delta down here. So we have two different deltas. None exist here, right? So, let's try to apply the delta to y conversion to the ABC triangle. And for that, we have to, and it's nice because I labeled the nodes ABC, so it kind of fits with our delta to y conversion. So let's go ahead and write out our values. So we have RAB, we have RBC, and we have RCA. RAB is 18K, RBC is 6K, and RCA was what, 12? 12K? All right, then let's go back and find our conversions. So we are looking at a delta to y conversion, which means we are here. We are using that. So the first thing let's do is, no, we're on the other side, sorry. We're here, on this side. Okay, so the first thing let's do, let's find out what our R sum delta is, with the because all of them will have the same denominator, right? RAB plus RBC plus RCA. And so it's 18 plus 18, so 36. Now let's go ahead and calculate what our RA, our RB, and our RC will be. And note that those names RA, RB, and RC, they don't necessarily make sense with respect to our circuit. They're more like definitions we're using as part of the delta to y conversion. We'll have to probably give them a better name when we inject them back into the circuit. Okay, so going back here again, the rest of the equation is simply, so for the first one, it's RCA RAB. So RCA RAB, so what's 12,000 times 18,000? Well, do you mind if I just write the answer? It's 6,000. For RAB, you have RAB, RBC over R sum delta. And the answer there is 3,000. And for this one, you have RCA, RBC over R sum delta. And the answer is 2,000. Okay? Those are just plugging in the values that we know. Now, what we have to do is make sure we cut the circuit properly, right? We're going to cut it along the dotted line. Leaving the three terminals, and now what we're going to do is we're going to plug in our Y right there. So what I'm going to do is I'm actually going to draw the rest of the circuit, leave the 3 terminals blank, and then we'll draw that in last. Okay, so the 4K ohm resistor and the 9K ohm resistor are untouched. This was the 9K, this is the 4K, this is and this down here is node D. This is untouched. And the 12 volts also the same. But now we have to put in a Y where we once had a delta. And so I didn't leave myself necessarily enough room. But we'll squeeze it in there. So now what we have is we still have our node A, we still have our node B, we still have our node C. We actually have a new node, which is the center of all of them. So I'll give him a new name, call him node E. Okay, and let's give the values that we calculated above. So this, the one associated with A is going to be RA, so this is 6,000, 6 kilo ohms. RB is 3 kilo ohms, and this is 2 kilo ohms. And now what we see is that these two are in series with one another, right? These two are in series with one another. You'll be able to combine them. The resultant, everything, will be in parallel, the 2 branches, and then that will be in series with the leftover 6K. So, like we saw in one of the other very preliminary examples, this will allow us, so this circuit can be solved using E and the 2 kilo ohms. All right, so what's left is to, do the parallel and series combos and solve. So we have this circuit here, right? And we just need to, the value ultimately that they asked us for is IS. So let's define an equivalent resistance, REQ, which I'm going to say is the equivalent resistance of everything altogether. And I can just write this out as one chunk. It's going to be 6 kilo ohms plus, we'll eliminate these one by one. So 6 kilo ohms plus the series combo of those two. So 3 kilo ohms plus 9 kilo ohms in parallel with those two, with 2 kilo ohms plus 4 kilo ohms. We know that this will be equal to 12K times 6K over 12K plus 6K. Can anybody tell me what that is? Someone say it? 4K? Is that easy to do in your head? I don't know. I can't do these things. Okay, so 4K plus 6K, and that gives us 10K. And then lastly, now we can calculate what our IS value is. IS will be equal to VS divided by R equivalent, which is, was it 12? 12 volts divided by 10 kiloohms, which gives us 1.2 milliamps. And so that's our final answer. Another example, another different flavor that we can add to these types of problems. And another one where we can boil it down to a single loop or single node pair and solve. If I wanted to, I could ask you for, so one really, I don't want to say tricky, but effort-intensive way to structure this problem would be to ask you for the current flowing along branch AB in the original circuit, which then would require you to solve for all the node voltages, which you would use Ohm's law for, and then do the conversion. Well, you don't need to do conversion back because you already know what the original values are, but then calculate the current. It wouldn't be that bad, actually. Go ahead.
You said the current along AB?
I take it back. That wouldn't be that hard. I was thinking that you didn't know the delta.
But like AB, like, isn't it two different things?
Exactly. I'm saying the current along the original configuration.
Oh, okay.
That was the key. What would be the current along the original configuration? Note that the current here, IS, the current flowing into that node doesn't change because, right, anything external to the delta or the Y stays the same. All right, so if I'm not wrong, we are done with chapter 2. So that works out well. So I'm going to start a new set of notes just because I think that's better. So great. No need to make any changes to what we're going to be examining for the quiz. Done with chapter 2. You have all the tools you need to solve the chapter 2 homeworks. We'll be diving into chapter 3 over the next 2 classes. And we'll go from there. All right. So, mesh and nodal analysis. So this is where things become both easier and harder. And so what does that mean? It provides us a very standardized way of solving these types of problems. You're not going to have to do the same amount of combining and re-expanding and all that type of stuff. It's sort of like you look at the circuit, you figure out what the variables are, you put them in this matrix sort of format, and then you use the linear algebra to solve. So that part is easy because I think it's more methodical. If you learn the method, if you learn the process, there are fewer points at which you have to make judgment calls. There's less of this stuff where we always say, well, there's a million ways to solve this problem, and algebra, it's sometimes going to be hard to combine the equations. That will be lessened here because it'll just be in the matrix, you invert the matrix, you multiply, and you solve. That being said, the ease of that is somewhat mitigated by the difficulty of the setting everything up. Okay, you have to get everything exactly right, signs are important, and the matrices will get big relatively quickly. We're not going to be doing any huge examples like 10 by 10 or 20 by 20 or anything like that, but we will get into the realm of like 5 or 6 node circuits where the admittance matrix, which we haven't learned what that is yet, but the admittance matrix will be 5 by 5. So, that's 25 elements that you got to fill in. Nodal and mesh analysis are actually both the exact same thing. They are, and there is an analysis. You can do analyses that use elements of both mesh and nodal together. So really, it's just a linear algebra approach to solving these circuits. So what is nodal analysis, which is the first thing we're going to talk about? It's based on using KCL to analyze the nodes systematically. So we know that we can set up KCL for each node, and we've been doing that, but this provides us a systematic way of solving. So we're going to build a system of linear equations and solve. And for solving, we can use substitution or we can use matrix math. You all are taking Advanced Engineering Math 1 in parallel with this course, right? I'm pretty sure that the way we restructured the course, it was supposed to have linear algebra at the beginning. Is that been the case? Before you do the differential equation stuff? Okay. Well, no process is perfect, I guess. The good news is I'll be giving you, I'll go through a tutorial of what you need to know for this stuff. But when you get to this point in ENG212, it'll help even more in terms of being able to do what needs to be done. All right, so let's take a look at what the general structure is going to look like. So what we have is we have a structure that's going to look like this. So let's say we have 2 currents that we want to solve for. They will be equal to something called an admittance matrix times the voltages. And I know this doesn't make much sense right now, but it will in a second. The main takeaway here is that this is just Ohm's law, right? We know V equals I times Z, and in a similar regard, I equals V times Y. This is the admittance matrix. And if you remember, well, okay, yes.
Does the underlining, is it for emphasis or does it actually mean something?
So this is like an older type of notation that not many people use anymore, but I learned when I was in college, where the number of underlines represents the dimension of the matrix. So vectors get 1 underline and matrices get 2 because this is a square matrix. It's not really necessary. The book doesn't use this notation. And it's not really necessary to understanding the problems, but gives you a clue of what I'm thinking. Okay, so first things first, let me spend a second talking about so I'm going to try to do this efficiently as possible. What that means is I'm not going to go into a lot of explanation of theory. I'm not going to give a lot of background. I'm going to try to just give you the bare bones of what you need in order to apply in this course, and then hopefully, not hopefully, ENG272 will fill in the blanks. So I think the best way to do this is I'm going to ask some questions, and let's see where people stop being able to answer the questions. So first things first. Let's say we have something that looks like this. Does everybody understand what we mean when we refer to them as 2 by 2 and 2 by 1 matrices, right? The first index represents the depth, the number of rows. The second index represents the number of columns. So 2 by 2, 2 by 1. What's the size of the product of these two? Corner.
2 by 1.
Yes, and the reason for that is you take the first and the last, and so your answer is going to be a 2 by 1. These had better match, because if they don't, you're not going to be able to do the multiplication, right? Now, let's get into the actual multiplying. There's only two values in this. What's the top value going to be? You give a lot of answers. We'll go through in the back.
A times E plus B times F.
Okay, good. And the reason for that is, right, what you do is you take, it's almost like you take this, you rotate it sideways, and you multiply it like that, right? It's like you imagine you take this and lay it on top. So the A lines up with the E, the B lines up with the F. I mean, obviously that's an informal way of describing it. The more formal way is to say that the first element is multiplied by the first element, second element is multiplied by the second element. Okay, so AE plus BF. And then for the bottom, you have CE plus D times F. Okay, so that's basic matrix multiplication. Matrix addition and subtraction, I don't need to talk about. You can only add and subtract matrices that are of the exact same size. And in that case, all you do is just add or subtract the elements. So if you have two 2 by 2 matrices, add this element to the 1 by 1 element, add this to the 2 by 2 element, 3 by 3 element, 4 by 4 element. Okay, now, if I have something that looks like this up here, okay, I equals Y times V, and you can see from the way this is set up that the admittance matrix will be a 2 by 2 matrix, right? Or else things don't work out. So let's say that I know this and I know this. Okay? How would we solve for V? Right, you can invert the matrix to solve. So what you end up with is V1, V2 equals the inverse of the admittance matrix times I1, I2. And that is going to be how we solve a huge chunk of these problems. You're going to have one vector worth of values, the currents or the voltages. The admittance matrix you're going to be able to define based on the structure of the network. And you are going to invert the matrix, the admittance matrix, and multiply to solve. I'm not going to go into too much detail now about inverting a matrix. You can only invert square matrices because you should be able to do this with your calculator. And since this is not really the focus of this class, going over linear algebra, I'll leave the manual methods for doing the inversion of a matrix to ENG212. It's not that hard. I mean, really, those are the bare bones of what you need to know for linear algebra to understand what it is that we're about to go into. There'll probably be some one-off things here or there that I'll go a little bit more into, but that's the essence of it, and those are the parts that we're going to use the most. So, diving back into nodal analysis. Really, the best way to introduce nodal analysis is by doing one. Okay, because what you'll see is it's just a little bit of a variation on what we've already been doing. Okay, we're going to set up the equations in a very similar way, and some people who are very comfortable with algebra in last chapter could have already been solving stuff in this way, but we're just going to formalize it now. So let's take a look at this circuit here. Oh, that's not right. Okay, so the goal here is to, and it's not explicitly written, but well, and the reason why I say solve for all currents voltages, is that in a nodal analysis, that is the value that it's going to first spit out, will be the node voltages. Okay, so without too much introduction, let's take a look at how to do this. Like we've done before, we want to label everything. For nodal analysis, as the name might suggest to you, it's really important that you label the nodes correctly. So what does that mean, labeling the nodes correctly? You can't forget a node, and you cannot accidentally label the same node as giving it two different names. So like if I did this, node 1, node 2, node 3, node 4. Node 3 and node 4 are the same node. If you start off with that, it's going to throw a huge wrench in your nodal analysis. It's essentially going to, every time you try to run the matrix math, it's going to, one of the expressions is going to be redundant, which means you're going to have a singular matrix, which means that every time you try to invert it, it's going to spit out undefined, and it keeps going on and on. It won't work. So it's very important that you label the nodes properly, and you know how many nodes there are. So in this case, we have 3 nodes. And you'll keep hearing the letter or the variable n referred to, nodal analysis problem where n equals 3. Nodal analysis problem where the number of nodes is equal to 3. Okay, next step. We need to take one of these 3 nodes, and one of them is going to become our reference, because we're going to be calculating the voltage between node 1 and something else, between node 2 and something else, between node 3 and something else. One of the nodes needs to be the reference, which a lot of people will say, well, that's the ground or that's the neutral. That's not necessarily true, because you can use other nodes besides the ground or the neutral as the reference, and the numbers still work out. It'd be an unusual way to do it, but so for most of these problems, it becomes pretty obvious what they intend for the reference node to be. Often at the bottom, there's one node that encompasses a lot of branches. It doesn't. I mean, we'll go through a lot of examples. It doesn't end up being, this decision of which node to use as the reference doesn't usually end up being like a big question mark. It's pretty obvious in a lot of cases. Okay, so we're going to choose 3. Which means that for our purposes, any place that we see a V3, we can consider that equal to 0. Because the reference, again, is the point at which it's our referential voltage point. Okay. Next, write out KCL for both non-reference nodes. And so now you're starting to see a little bit of the value of this nodal analysis. We're not questioning which equations we're going to use and how we're going to combine them. It's pretty linear and methodical process that we take. So KCL for the two non-reference nodes, that is going to look like this. And so, again, I don't have to label everything because we can just use the names. But, right, I'll call this I21, I31, I12 would be heading in the other direction. Okay, so let's write out for node number 1 what we have, and I'm going to take the reference direction heading into the node as positive. So, why don't I ask you, what's define KCL for node number 1? Yes?
IA plus I31 plus I21.
Mm-hmm. All right, and then for node number 2, it seems like you guys have a handle on it, so there's no point in dragging it out. So for the node number 2, I'm actually going to use, I'm going to keep it consistent. I'm going to use the same referential direction. So heading into the node will be positive. So IB minus I could say plus I12 plus I32 equals 0. Okay. So the number of equations that we have to solve, which then ends up being the size of the admittance matrix, as well as the height of the voltage and current vectors, is equal to n minus 1. All right, so we have 3 nodes. That means that the 2 equations to solve, and the admittance matrix will be a 2 by 2. One thing I'm going to do real quickly is I'm going to move the known sources to one side. So we have IA equals negative I31 minus I21, and then we have negative IB equals minus I12 minus I31. And I'm going to try to maintain positive current means heading into the node. Because if you look, I could have taken this second equation, I could have said IB is equal to I12 plus I32, right? Which at first, it's like, well, that looks nicer, right? There's no negatives. But the reason why I want to keep it this way is because later on, we're going to learn a method of doing nodal analysis where we don't write down the equations at all, which is going to be called nodal analysis by inspection. So you just look at the circuit and you go straight to the matrix. When we do nodal analysis by inspection, there's certain assumptions we make, and one of them is that the current's positive when it's heading into the node. So in order to make what we're doing now agree with what we'll be doing then, let's just go ahead and try to stick with that. Okay, now let's substitute for Ohm's law. We have IA equals minus 1 over. So for R3, 1, it'll be does everybody see why that is? let's take a look back up here. So we're dealing with I31, which is right here. So that's going to be V3 minus V1 over R1, right? V3 minus V1 over R1, and the negative comes from the fact that it's already negative up top. All right, hopefully the rest of these we can do a little bit more quickly. So we'll have 1 over R2, V2 minus V1. Negative IB equals negative 1 over R2, V1 minus V2. Note here, the directions and the order of the subscripts corresponds to how we use them below. I21 is calculated using V2 minus V1 because the direction is node 2 to node 1. I12 is calculated using V1 minus V2 because the direction is I1 to I2. So as we move into these types of problems, we're going to start labeling less and just relying on the double subscript notation to tell us what everything is. And again, it's up to you how quickly you want to jump into that method. And lastly, we have 1 over R3 is V3 minus V1. No. That's a mistake. And for this one, there's a little bit of ambiguity because there's actually two I32s, right? There's two parallel branches, so I'll label that one to indicate which one we're talking about. And maybe I should give that a prime or something. All right. So now we're almost done here. So let's pull out the voltages or separate by the voltages. Before I do that, I'm going to cross out anywhere there's a, well, not that much because I want people to see it. I'm going to cross out anywhere there's a V3, right? Because we know V3 equals 0. So now I have IA, I have negative IB equals. So let's collect our elements by V1. So by V1, what we'll end up with is 1 over R1 plus 1 over R2, if you account for all the negatives and stuff. Yep?
How do we know that V3 is 0?
Because up here, we set it as the referential node, meaning that it's the only one that gets the lucky. The benefit of being called a 0 always. Okay, then V2 will be equal to negative R1 over R2. Down here we'll have V1. And that will have 1 over negative 1 over R2. And then we'll be left with V3, which will be 1 over R2 plus 1 over R3. We're almost done. Or we're almost at a good stopping point. That should be V2. Sorry, V2. What's happening is it's a side effect. So when you learn the inspection method, you start already knowing what the answer is going to be before you write it. So like I'm doing it ahead in my brain and not paying attention to the math. Sorry. Yes, it's V2. Okay, so, and this is the form which we set out above and said we were going to use, this one here. So let's go ahead and set that out. So we have IA negative IB equals something, leave that open for a sec, times V1, V2. And now we plug in the values. It's going to be a 2 by 2 matrix, and after we define the matrix, we'll stop. Right up against the wire. So what is the 1, 1 element? So first things first, think about it as this equation corresponds to this row. Think about it as this equation corresponds to this row. Yeah. Say it again?
1 over R1 plus 1 over R2.
Yeah. Next one.
Negative 1 over R2.
Right? Because we see, I'm trying to wrap up quickly, we see that both of these elements all right. We'll stop there. Next time, we'll finish up. Okay? But at least we got to the point of taking the system and putting it into the matrix form, which is the hardest part.
I don't understand why I think it's 1 over R1 plus 1 over R2.
Okay? Specifically, it's that element right there. And then so if we go further up, here, there's two coefficients of V1. There's 1 over R1, there's 1 over R2. Both of them have double negatives, so they just cancel out. So what you're left with is V1 times 1 over R1 plus 1 over R2. It just